Well, good morning, good afternoon, and good evening. Welcome, everyone. Thank you for coming to my invited talk on machine learning and artificial intelligence in PEM fuel cell development. My name is Yun Wang from UC Irvine, and I'm affiliated with mechanical and aerospace engineering and the renewable energy resources lab. And I want to take this opportunity also to introduce recent two works or books from my lab. One is PEM fuel cells, and the other is water and thermal management of PEM fuel cells, which was recently published. We also want to share with you recent review of our work on fundamentals, materials, and machine learning of PEM fuel cell technology, which was published in Energy and AI last year. So my invited talk today will primarily based on this review papers, data, and analysis. In this talk, I will first give an introduction to PEM fuel cell technology, and then the R&D recent progress, and the machine learning and the artificial intelligence, and the machine learning and AI in fuel cells. And especially, I will introduce 4 case studies, including CNN, imaging analysis, an ANN model to predict fuel cell performance, and a genetic algorithm coupled with ANN or SVM for fuel cell material and control optimizations. I will also discuss machine learning and AI resources and opportunities for fuel cell R&D. At the end, I will conclude my talk. So this is a fuel cell structure and a very standard, and you will see catalyst layer and the channel, and also the reaction for anode side and cathode side. And you see the hydrogen and the water are injected in fuel cell. And you will also see the electrical power, water, and waste heat are produced. The table here, I put the fuel cell with other type of fuel cells. Example, the solid oxide fuel cell, molten carbon fuel cells, and others. Compare them side by side, and they maybe operate under different temperatures, use different materials. And so again, for PEM fuel cell, we use the polymer membrane, and can operate -40 to 120 degrees C, and come up to 65 to 72% efficiency, and use hydrogen, and the primary application for portable transportation and stationary. In 2019, I have the data, and you see PEM fuel cell are the major fuel cell type which receives the most R&D efforts. This slide, I summarize, I put together a fuel cell structure, materials. This is for the channel flow field for hydrogen and oxygen flow. This is the gas diffusion layer. This is the catalyst layer and membrane. This is the catalyst layer nano structure, and this is the membrane molecular structure. So we put them together, and we will find ourselves fuel cell stack. So there are a few number of fuel cell put together, and this stack needs some, for example, the boost converter and the hydrogen circulating pump to make a fuel cell engine. Then we put the engine in a car or bus and to power the vehicles. And now, in the past few years, and you will see a number of fuel cell vehicles, for example, Toyota Mirai and Hyundai and Honda and also a few fuel cell bus operating on the road. And this shows the fuel cell power shift by years. You see, among different type of fuel cells, you see the PEM fuel cell and has the most R&D effort compared with others. And this table summarizes the fuel cell vehicles. And by 2019, you see there's 8,000, 5,000, 3,000 in US, South Korea, Japan, respectively, and 2,000 in Europe. And by 2030, there will be some goal targets, 5.3 million, and million almost for South Korea and Japan, and 4.2 million in Europe, and 1 million in China. So again, this is a fast-growing market for fuel cell application. In this slide, and I presented a comparison of diesel or combustion-based bus versus fuel cell or based bus, which is powered on hydrogen fuel. Now, this side you see diesel. Now, this fuel cell bus is on campus of UCI and operate 24 hours, 7 days, and it's cost UCI over $1 million, and for students to experience the new technology. Now, on the side, this side is the input to the vehicle. You see diesel plus air, and this is hydrogen plus air, you see, and the hydrogen fuel cell uses less or more than half air, and this is for 1 year operation. And I think comparable in terms of operation hour and also the distance. So for the output, you see a number of carbon dioxide, carbon monoxide, NOx, and even the particulate matter, and for diesel engine, and for hydrogen, and only water and some unused oxygen and nitrogen. So you see from the comparison, you see the clean power and the zero emission technology that's enabled by PEM fuel cell technology. Another barriers to fuel cell vehicle application is the hydrogen refueling station availability. So this gives a hydrogen gas station structure. And so apart here, because this is gas refueling, so the refueling can take 3 to 5 minutes, which is comparable with traditional gasoline refueling, but much faster than battery recharge station, which it takes about 20 to 30 minutes. And this picture shows the California hydrogen refueling station map. And for this gray area, there is no hydrogen refueling station available. So if you have a fuel cell car, you need to drive to those colored area to refuel your fuel cell vehicle. Now, this table summarizes the number of hydrogen station by September 2020. It's in United States, and we have 44 stations. Most of them are in California, in Germany, 85, and Japan, 133, and South Korea, 34, and China, 52. And 2030s, there's some goal, and you see some rapid growing, in United States, over 1,000, and in Japan, about 1,000, and South Korea, 500, and China, 1,000. And this is try to develop the infrastructure and for customer to use to refuel their fuel cell vehicles. Now, machine learning and AI, I quote some words from our previous president, Donald Trump, about the importance of AI in our economic and national security of our country. So again, there are a number of agencies in DOE and give the funds the AI development. And this figure shows the patent, AI patent related. And by years, you see in recent 10 years, and it increases dramatically. And this structure shows the deep learning, machine learning, and artificial intelligence relationship, and which is given by the DOE. This slide, I would like to show the relationship between fuel cell and machine learning and AI. And basically, this part, the red table shows the fuel cell fundamental materials. This blue one shows the fuel cell application. Now, for both sides, you will see a relationship with machine learning. We use this neural network as an example. Now, where we can get data from the fundamental side, and the machine learning and AI can improve fuel cell performance and materials and imaging analysis. And in the application side, and the data, operating data can put into a machine learning for learning, and the machine learning and AI can provide fuel cell control, hybrid design, and optimization. There were a number of machine learning and AI research in fuel cell. And here I use 4 as an example. One is to optimize the channel or parameters that show up here. And this is a channel where the channel width and the distance. And this picture shows the comparison between artificial neural network and this kind of this supporting vector machine learning. And this also provide, I think my colleagues in Tianjin University studying a single fuel cell with a single channel, 3 serpentine performance, and this to predict the fuel cell power signal. In our review paper, and we summarize recent work of machine learning and AI in fuel cell, and you see the AN and SVM and other methods. And again, this table, there are more tables in the paper, and the targets and the details of machine learning and the references. We also summarize the machine learning and AI methods for fuel cell R&D. And from the table, you see some neural network and the short-term memory and some kind of the particle filtering methods here. And there are some kind of characteristics along with some work, recent work using the methods in fuel cell study. Now, in the following, I would like to use a few case studies which are active in my lab and to investigate fuel cell fundamentals and the application. So the first one is to study the two-phase flow in fuel cell. Now, in fuel cell, and water is produced in the cathode side by the oxygen reduction reaction. If there are too much water, you're flooding in the fuel cell, and oxygen won't be able to get to the catalyst layer, and the fuel cell won't work very well. And the optical imaging shows the liquid water in fuel cell channel from the gas diffusion layer or the catalyst layer. And this shows the water contents in a fuel cell by neutron imaging and the 3D modeling. And this shows the water produced, liquid water produced, and flow from the gas diffusion layer and removed by the channel flow. And this is the liquid water under land versus under channel under different current density operation. So neutron imaging is a very effective methods to visualize liquid water in the PEM fuel cell, because the neutron, thermal neutron are very sensitive to liquid water versus the other materials, fuel cell materials, such as the aluminum or carbon. So again, this shows the neutron beam, so operating fuel cell, and we get the liquid water. And this shows the water imaging and under different current density and the different configuration. And with this imaging, we can put in a convolutional neural network, and by learning, we can output the water contents in the fuel cell. And this again shows this kind of the symbols compared with literature data, and show a very good agreement. And the work results methods are summarized in our recent paper submitted to energy conversion and management. Now, the second case study to predict fuel cell performance. Now, fuel cell performance is governed by a few mechanisms such as crossover, activation loss. And this is not, I'm sorry, this typo, this is actually the ohmic loss, linear drop. This is a mass transport loss. And these loss are related by material or fuel cell. I show some material here, and this shows the different curve of fuel cell performance. We like to see a higher voltage under a specific current. So again, over here is the fuel cell performance is governed by a few parameters, and we normally use experiment, measurement, or physical modeling to get the fuel cell performance, and which is time consuming normally, and we want to try to see how machine learning or AI methods and for fuel cell performance prediction. So in fuel cell machine learning modeling here, and we use the neural network, neurals, and the input layer, we use the parameters, okay, data, and from a 3D model over 1,000 data, and from the learning, I use the BP algorithm, and plus a transfer function, and we will predict the voltage. And this is a different type of the condition, and this is the convergence of iteration in machine learning, and this comparison in the testing data, and show a very good agreement. And so in addition to our work, there are other people working in the same area, including some colleagues in 2004. So with the fuel cell performance learning, then we can further coupled with genetic algorithm and to predict the maximum power or the maximum power condition. So again, this is the genetic algorithm, which is biological evolution is optimization methods, and you will see the crossover mutation, and where we couple with the AN. The AN learn from the multi-physics model, and then this kind of the GA structure to optimize this set of the parameter and for the maximum power output. And this is showing the comparison with input data, and this where you see the fuel cell can achieve a maximum about 0.8 watt per centimeter square power. And we also apply this measure to identify the maximum achievable power under different temperature, which is very important for practical application. As you see the red curve. Okay, so again, not the highest temperature will give us a highest peak power because of the water management. And you see the best temperature, the maximum power is around 360 Kelvin. And we also identify the relative humidity operation for anode side and the cathode side and use the methods. And we also apply the machine learning and the GA to optimize material of fuel cell, which is a porous emitter flow field. So porous emitter flow field, where we put a porous emitter in the channel and provide some advantages. For example, the best electron conductivity, and also heat transfer, heat removal. And these materials can be used such as metal foam and carbon paper, And this is the Toyota Mirai, which is a recent commercialized fuel cell vehicle, which adopts the porous emitter flow field in the cathode side. And the one part here is the porous emitter permeability and versus porosity, which is important to manage the pumping power to a fuel cell. And again, the porous emitter flow field shows improvement in fuel cell high current density performance, and because of the improved mass mixing and mass transfer characteristics. And this show our study, and we use digitally constructed porous emitter structured, we call it the metal mesh, and in a fuel cell model. And you see here, you see the space between the mesh and the diameter of the rod. And so again, this simulation coupled with electrochemical reaction. And you see the line here shows the reactant flow. And again, with this rod, and this will increase the mass mixing in the channel. So again, we use the different diameter fiber and the distance and the parameter, and we get the data from the model. And then we put this table and to machine learning show up here. We use the support vector machine and to learn those data and couple with the genetic algorithm for all the parameter DS optimization to get the maximum power current density. So again, this shows this kind of the prediction and for the GA and SVM, and we can also get this kind of ohmic resistance, okay, and under different porosity and the space, fiber space. And again, this shows the porosity, current density, and again, the results and the methods are summarized in our recent paper in energy conversion and management. For opportunities, and we put this kind of the parts, the fuel cell performance, material optimization, control over here to make this happen. We believe that's fuel cell physics needs to incorporate it in machine learning and AI. And we summarize a few major fuel cell components. There are major physics, such as ion transport, where is the Nernst-Planck equation, and where we have two-phase flow, and also the Ohm's law. So again, those one is to be incorporated in machine learning or AI in order to better predict fuel cell performance and develop materials. And again, there's a target material for each component. And again, the equations here, not given here, but it's in our recent review paper. So we also summarize the professional machine learning tools available for R&D for energy and materials, and follow Butter paper in Nature. And again, you will see the link, and you see the description of the packages. So again, we think those materials are important and for fuel cell R&D. In conclusion, PEM fuel cells are promising future power source for portable automobile and stationary applications. And the fuel cell vehicles have been successfully commercialized, and the cost, durability, and the hydrogen infrastructure are main barriers to fuel cell vehicle broad deployment. Machine learning and AI are powerful tools in fuel cell R&D, and the various AI resources were summarized. And the CNN, AN, and the GA models can be applied to analyze in situ imaging, fuel cell performance, and optimization of fuel cell materials and control. And opportunities exist for machine learning and AI in fuel cell R&D, such as physics-informed learning, material design, control optimization. With that, okay, I would like to thank you and for attending my talk and presentation. And if you have any questions, and please feel free to drop me an email or visit our website at uci.edu. Thank you.